Okay. Hi guys. So actually I guess this will be our last class. I guess they changed the last day of classes at some point to today, which is actually fine. But let me just try to give you an idea of my plan. Okay. So let me just tell you some of the things. Right, so today we're going to finish up what we need. That means we need to talk about a couple different things. We need to talk about polynomials in polynomial rings over a field. We need to talk about this. I want this to focus better. How do I? Okay, that seems okay. Okay, so polynomial rings over a field. We want to talk about how the ideals in a polynomial ring over a field, they're all principal ideals. So a polynomial ring over a field. Okay, we usually write it like if K is a field, we write it like K of X, like that. K of X is, we want to know that it's a principal ideal domain. We'll call that PID. Meaning, if you have an ideal in this ring, it is automatic, it is principal. Okay. Oh, I missed someone in the waiting. Okay. Okay, once we know that, we can talk about the difference between an irreducible polynomial and a prime ideal. Okay. And then once we do that, I think we should be able to do that in 1 hour, and then the next hour will just be like kind of examples. Okay. So the idea is that if you take an irreducible polynomial, you can use that to get a field where the polynomial has a root. Okay. We'll talk about that more when we get to it. Okay, let me tell you more about the plan in general. So this is just the plan for today. Oh yeah, and then the last part of the plan is just examples. Okay. And I want to make sure, so in this plan, this is enough that I feel comfortable with, like kind of concluding the class and just saying like, we'll do more, I'll post more worked examples in video form. Okay, so let me tell you the part of the plan this is just for today. But let me tell you the plan as far as like what you can expect as we move on into like the break before the exam and stuff like that. Okay. So what can you expect from me? This like last kind of practice problem set, which can be viewed as just like practice for the final exam. Okay. Especially this problem set, the focus will be ring theory. Okay. I'm trying. Okay. And then I want to be posting videos with work problems. And if you feel, you can feel free to request me to work out certain problems that are giving you trouble, you know? So, okay. Let's see, what else I need. I also will give you video solutions to the coursework exam, which was just on Wednesday. Okay. And then, okay, this is all good. And my most immediate thing would be marking all, just all the material so that I can give you your kind of your grade going into the final as soon as possible. Okay. And oh yeah, and I should tell you, once I get all your grades, like the coursework grades finalized, you can go. So once these are done, well, I'll put an announcement on my learning, but you can go to check your grades when they're ready. You have to click on this box in my learning that looks like that. So you click the box. Oh yeah, so this is for the grades. You click this box, and then I think like a menu comes down, and you have to click on, I think one of them is grades. And then there'll be like, it'll show all your assignments and coursework exams. And then I will put, like the very last thing will be, you have to look for an item, which is like total, it'll be like total coursework mark out of 50, something like that. And then your mark will be whatever it is, like maybe 39.55. That means that you're going into the final exam with 39.55. And then it'll have some other things which kind of which I can't seem to get rid of, and you just ignore those. Okay. But when I post the grades, if you have any questions, just let me know. I'll try and clear everything up. Okay. So before I get going with with polynomial rings and things like that. Are there any questions? Any concerns? Oh, I can answer that. How many questions oh yeah, and okay. I'll answer your question and then I'll give you some more information. How many questions does our final exam have is the question? And it has 7 questions. So let me tell you about the structure of the final exam. It has 7 questions. And recently they approved a certain structure, like a certain structure for the final exam, which I will tell you about now as well. So there's so the final exam, you'll have a 12-hour window. No, sorry. 12 hours, but you have a 3-hour window inside of 12 hours. I mean, how do I phrase this? So a 3-hour window inside 12 hours. Okay, so the final exam will be scheduled for some 12-hour period, whenever it is, I don't know. And then you have to choose, I mean, you don't have to choose, but once you start your final exam, you have 3 hours from when you you know, open up until you submit. Okay, so you have 12 hours. I am not aware when the 12 hours will be yet. And then, you know, you decide, like, maybe from 2 to 5, that's when you are gonna do the best. That's when you have. Someone else decides they work best from 8 till 11, that's when they have. Okay. I know this is not how we did the coursework exams. It's just because I guess they wanted it to be more similar to how the other exams were. Okay. Any other questions about the final exam? Okay. And I'll just note, yeah, okay. So okay, so let me now, let's try and get with let's go back to our outline. Let's try and talk about this polynomial rings over a field. Okay. Okay, so we just need a definition. Probably I don't need to define this for you, but I'll still define it. Okay, so we have a field K. Remember what that means. K is a commutative ring. K is an integral domain. But so that means that you know, that means if you have A, B equals 0 in K, it means either A is 0 or B is 0. Okay, but furthermore, any non-zero thing has an inverse. Okay. So that's what a field is. For example, you know, there's a bunch of fields: the rational numbers, the real numbers, the complex numbers, and what's another idea? You also have the finite field with 5 elements, for example, which is just another name for the integers mod 5. Okay, so the integers mod 5 are a field. Everything that's non-zero has an inverse. Okay. Okay, and then, you know, K is going to be a field, and then we can just construct a ring as follows. So we define K of X is just going to be the set of all the polynomials with coefficients in K. Like that. Okay, a polynomial has a bunch of coefficients up to x to the n, such that all these coefficients are in the field K, n is greater than or equal to 0. Yeah. Okay, and addition of polynomials is just how you would expect. Just by gathering up the x's. Multiplication of polynomials is also just like the kind of obvious thing. Well, obvious if you remember, but you know, like, how do I multiply 1 plus 2x times 3x squared plus 5x to the fourth? Well, I just expand everything, and then I just say that x times x squared is x cubed, and things like that. If I expand it, I get 3x squared plus 5x to the fourth plus 6x cubed plus 10x to the fifth. That is just how you would naturally do it, I guess. Okay. So you define addition and multiplication, you get a ring. Okay. Now we need to know a few things about this ring. What's the first thing? Let me move this up. Okay, so this ring, you know, let's just like write down some things about it. Okay, so let R be a polynomial ring. Okay. Then every polynomial has every non-zero polynomial has a natural number associated to it called the degree. Okay, so define for 0 not equal to f of x. Define the degree of f to be n, where f of x is a0 plus a1x all the way up to an x to the n, and an is not 0. Okay, so we have this notion of degree. As an example, the degree of 1 plus 2x is 1 because 1 plus 2x, you can write it as 1 plus 2 times x to the 1. And so a1 is 2 and 2 is non-zero. So you have like, so it's just picking out the highest term in f. What about, you have degree 3x squared plus 5x to the 4th. Well, that's 4 because the highest term, the highest order term is x to the 4th. Okay. Of course, the degree of our example, when we multiply them, the degree was 5, and actually that's just 4 plus 1, and that is not a coincidence. Okay, so we get a basic property of degree, which we won't prove, is that so we have things like the degree of f plus or minus g is less than or equal to the maximum of the degree of f and the degree of g. Okay, let's see, the degree of f times g is equal to the degree of f time plus the degree of g. Okay, so that gives you a good idea of how the degree behaves. Okay. Okay, and as a corollary to this, okay, as a couple corollaries, you get that k of x is an integral domain and the units of k of x needing the polynomials which have multiplicative inverses. Well, those are just the non-zero scalars in k. So it's such a a0 is in k, and a0 is not equal to 0. In other words, that the units in k of x are the polynomials with degree 0. In other words, the constants or the scalars. Okay. Okay, so the reason I say this is a corollary is because you know, if f and g are non-zero, then their degrees are well defined. But if f times g is 0, then this is not defined. Okay, but you know, so you can't. Yeah, it just says like when you multiply two polynomials together, you get a polynomial with higher degrees. So you can't like suddenly get 0. Okay, and another example, how do you show that the only polynomials which have inverses are the constants? Well, if f times g is 1, the degree of the constant polynomial 1 is 0. The degree of 1 is 0. And in order to have degree of f plus degree of g equals 0, well, these are both natural numbers. They're both greater than or equal to 0. So the only one way to have their sum equals 0 if they're both 0. Okay. So the only way to multiply two polynomials to get 1 is if the two polynomials are just constants. Okay. Okay. So let's talk a little bit about the ideals. Well, before we do that, let me remind you, or just tell you about the division algorithm. Okay, so just like we have, we can divide integers. We can also let me leave that. All right, we can divide polynomials. Okay, so we have this proposition. It's called, we could call it the division algorithm. The proposition we call it the division algorithm, but it's really like the fact that there exists a way to divide polynomials. Okay, so let A and B be polynomials. And we'll have that A is not equal to the 0 polynomial. Then there exists polynomials Q and R such that B equals QA plus R, and either R is equal to 0 or the degree of R is less than the degree of A. Okay. Okay. So we're not going to prove this, but we can at least do an example. And the example is just kind of like how you divide polynomials is just like you kind of just imitate how you divide natural numbers, you know? So I'll show you what I mean with an example. Okay, so I have two polynomials I want to divide. I want to divide x squared plus 1 into like some polynomial like okay, let me write down this polynomial, and after this example, I guess we should probably take a break. Something like that. Okay, notice when I divide, I include a place for every possible degree up to the total degree of the polynomial. So even though this is a polynomial x to the 5th plus 4x to the 4th plus x squared plus 5, I include the x cubed and the x places. And you just think about that as being, oh yeah, this is really the polynomial x squared plus 0x plus 1. But the reason for that is just because, you know, when I am dividing, when I'm dividing into this number, I don't skip over the zeros. I have to put them in. It's the same reason. Okay. Then, so you can kind of like roughly, this is like a polynomial in the variable 10. Okay, that's a wrong thing to say, but like give you an idea of what we do. So we take here, we divide this into this. Well, we try to match up the highest degree terms. The x squared goes into x to the 5th, x cubed times. We just put an x cubed. And then we multiply. and we get x to the fifth, x cubed times 0x gives me 0x to the fourth, and then 1 plus x cubed. And we subtract. And it's just like the same thing. When I divide 101 into this, I get, it goes in one time, and do like that. Okay, so I'm basically doing like the same thing. The arithmetic isn't exactly the same as you'll see, but that's fine. Okay, and now I subtract x to the fifth minus x to the fifth gives me 0, and then I get remainder of 4x to the fourth minus x cubed. And now this goes into this 4x squared times. And so I go on like that. I multiply. And I'm always choosing this to match up with the highest term, and so that the constants like match up with this constant, you know? Okay. And then I get plus 0x cubed. And then I get plus 4x squared. And when I subtract, I get minus x cubed minus 4x squared. Oh, sorry, I made a little error. I get x squared minus 4x squared. So I get a 3. And I keep on going. Now I have a minus x. And then I get minus 3x squared. 0 minus x is plus x. And then I have minus 3. And then minus 3x squared minus 3. So I have a remainder of x plus 5 minus 3. I get x plus 8 as my remainder. Okay. So this is Q. This is R. Notice that the degree of R is 1, which is less than the degree of A, which is 2. This is A. This whole thing is B. Okay. Okay, so we're gonna stop with that. Well, we're gonna like take a little break. After the break, we'll keep on talking about polynomial rings. We need to talk about, because we have the division algorithm, basically a lot of things that we can do with the integers, like we have prime numbers, we have GCDs, we have quotient rings, all of that stuff we can do with polynomial rings too. Okay, so we'll see some of that coming up. Okay, any last questions before I stop this recording and restart? Okay. So yeah, let's just take a break for 5 minutes. Okay. Okay.